Welcome back to our geometry series. Today we are up to section 7.4 where we'll be looking at the area of regular polygons. We can classify polygons a couple different ways. In this first example, it is equilateral. This first shape has four sides that are all the same length. That means it is equilateral. In the second example, this rectangle is equiangular. All four angles are the same. In this case, we have four right angles. The third example is a square. It is both equilateral and equiangular. In the fourth example, it is neither equiangular or equilateral. It's just a shape. A polygon is considered regular if and only if it is both equilateral and equiangular. So this square is a regular polygon. Let's take a look at this regular hexagon. Without having to draw extra shapes or symbols, calling it a regular hexagon means that all six angles are the same and all six sides are the same. Next, we're going to put a circle around this hexagon with center O. This point O is the center of a regular polygon if it is the center of the circle circumscribed about the polygon, meaning the circle just fits around the edges and the vertexes of the polygon. Next, we'll draw the radius from the center of the circle out to its edge. In this case, a radius of a regular polygon joins the center to a vertex of the polygon. It just also happens to be the radius of the circle circumscribed about the polygon. Next, we're going to draw this weird line from the center down to the edge of the polygon. This is what we call an apothem. An apothem of a regular polygon is the shortest distance from the center to any side of the polygon. Sometimes this is pronounced apothem, but I prefer apothem. Let's draw another radius here next to the first one we drew. This is what we call consecutive radii. They are radii that touch two consecutive vertices of the hexagon. Now let's take a look at the angle created by these two radii. An angle is a central angle of a regular polygon if its vertex is the center of the polygon and its sides are consecutive radii, like we have here. And that leads us to Theorem 87. The area of a regular polygon is equal to 1/2 the product of the apothem and the perimeter. So area equals 1/2 A times P. Now notice I've used two different letter A's here. The capital A is for area, the lowercase a is for apothem. So here's an example of a regular hexagon where the side is 8 and the apothem is 4√3. Remember, the perimeter is the sum of the lengths of all sides of a polygon. And since we have a regular hexagon, every side must be 8. Therefore, the perimeter is 48, 6 times 8. So we can substitute that in. The area is equal to 1/2 times the apothem, which is 4√3, times the perimeter, which is 48, and that gives us 96√3. Now let's move the central angle down here to the bottom of this hexagon, and redraw the apothem. In this case, the apothem both bisects the central angle and it bisects the side of the polygon. So here you can see we've created two smaller angles that are congruent to each other and two smaller segments that are congruent to each other. Let's jump over the whiteboard and do some examples. All right, we're going to draw a regular triangle over here as best as I can. So all the angles are congruent and the three sides are congruent. And we're just going to write down here what it is. A regular triangle. So that saves us putting the lines and showing all the angles being congruent. Now what we're going to do is say that this side is 12 and the center, which is about here somewhere, and we're going to draw the apothem, maybe a dotted dashed line something. It's going to be perpendicular to a side, and that the apothem is 2√3. Now I see a lot of these square roots because we've got 30, 60, 90 triangles, and this root 3 will come from time to time. Let's make that center nice and juicy. So what is the area of this regular triangle? Well, because it's regular, we can use that formula where the area is equal to 1/2 the apothem, lowercase a, times the perimeter. So we can just rewrite this as 1/2 apothem, which would be 2 root 3, times the perimeter. Well, we know one side is 12, but again, because it's regular, this has to be 12, and this has to be 12, so 12 and 12 and 12 is 36. And we can expand this out. 1/2 and the 2, that's going to cancel itself out. And we end up with 36 root 3. Now I'm going to slide another one down here. Just try to squeeze this in here. I'm going to draw a regular octagon. 2, 3, 4, 5, 6, 7, 8. 8 sides. Okay, so I'm going to, this was the regular triangle up here, and this is a regular octagon over yonder. And we're going to say that this side here is 10, and we're going to make a nice juicy center, and we're going to draw an apothem this way. Again, it doesn't always have to be down, as long as it's perpendicular to a side, which would be the shortest distance to the side. And this apothem, we'll say, is 12.1. That's nice and fun. So we'll use the same equation again. We'll just kind of put it up over here. Area equals 1/2 apothem times perimeter. So we'll write as 1/2 times the apothem, which is 12.1, times the perimeter. Okay, so we've got 10 here, but because it's regular, we know that this is 10, that's 10, 10, 10, 10, 10, 10. So we have 8 sides times 10 is 80, like this. So if we do up all the math here, 120 times 8, we get up Mr. Calculator if we need it. This ends up being 484. Now, let's just say we had units here. Let's say this was 10 inches and this was 12.1 inches. Now we need units on this answer. So this would be 484 square inches. It's important to have the right units, and because we're talking about area, we're talking about all the space filled in here, it would be square inches. All right, let's clean this up and do some more examples. Okay, we're going to go up here, try to get as far over as we can. We're just going to draw a square, which by definition is a regular polygon, not the best drawn square you've ever seen. And we've got a nice juicy center, nice caramel center there. And we're going to say that the side over here is 14 feet. And I'm going to draw out to a vertex here. So this would be a radius. If we drew a circle, circumscribed about, it would be the same radius as this. And we can call it center O if we wanted to. And then what we're going to do is also draw an apothem over here. So what I want to know is, we want to find the apothem, the radius, and the area. So we're going to try to find all three of these things with only this one piece of information over here. So this center of the square is equidistant from this side to this side. So if we were to draw, say another apothem over here, right? This could be an apothem. So whatever this is the same as this. This apothem has to be the same as this. So this apothem is halfway across the square. So the apothem has to be 7 feet, right? So 7 feet this way, 7 feet this way equals the 14 that is the same as the side. So that was pretty easy. Now we've got this weird thing going on here with the radius. I'm going to try to blow it up a little bit down here, right? The apothem is 7, and we've got, again, half of 14 here. So this side is 7, that's 7. So that's 7. So we're trying to find out what this R here, radius. So this is actually a 45, 45, 90 triangle that we've made right here. So from our previous experiences, we know that this radius is going to be 7 root 2 feet. So we'll put a handy little formula down here. We know that the area of a regular polygon is 1/2 apothem times perimeter. So we have 1/2 times the apothem, which we know is 7, times the perimeter. Okay, perimeter is 14 plus 14 plus 14 plus 14, or 28 plus 28. So if you add all those up, you get 56. So again, we can use Mr. Calculator to figure this out to be 196. Again, we're talking about area. We're talking about this whole filled in area. So the units need to be square feet. For our last example, we're going to go back to a hexagon, assuming I can draw it fairly well. This is a regular hexagon. Well, that doesn't look, we're going to write it down because I drew it so badly. Regular hexagon. All right, so all the sides are the same, all the angles are the same. And we're going to put point O, and I'm going to mark some other points. So we're going to draw an apothem here, and we're going to draw a radius here. So radius, apothem, and we're going to know that the side is 10. We want to know the same things. We want to know the area, the apothem, the radius, and the area. And just so it's a little clear, I'm going to mark some points here. I'm going to mark this R, and this point where the apothem comes down is P, and this over here is D. And I'm going to draw another radius. All right, so we got a radius, radius, apothem, and a radius. So how do we do this? Well, we know that every side is 10. So we know that right now the perimeter is 60. Okay, so we're going to use that later when we get into the area. But how do we figure out the rest of this? So if you imagine we made radii all the way across, right? And we went all the way around this circle. If we had an inscribed circle, we have 360 degrees all the way around. Because this is a regular hexagon, this angle has to be the same as this angle, as this angle. So we've got like 6 pieces to a pie here. We've got 360 degrees all the way around. So what I'm going to do is I'm going to blow up one of these corners again down here. So we're going to take RPD, this triangle. I'm going to try to draw it a little better. So here's O, and make it as big as I can, still staying on the screen, like this. Here's R, and we're going to draw this apothem, P and D. I'm looking at this angle right here, right? So we got 360 degrees all the way around, and there's 6 of these pizza slices. So this angle here, ROD, angle ROD, has to equal 60 degrees. 60 all the way around times 6 would be 360 degrees. We also learned that this apothem will bisect this angle. So ROP, angle ROP, that's terrible, ROP, will be congruent to DOP, angle DOP. So we're taking this 60 degree angle and cutting it in half. So this is going to be 30 and this will be 30. Now again, this triangle is equal all the way around. So this has to equal 60 and this has to equal 60. You can see what's happening here. We have a 30, 60, 90 triangle. And we know that one side of that triangle is 10 because this is the bottom half of this hexagon because all these sides are 10. And again, this apothem will split this side in half. So RP is 5 and PD is 5. And because we have this equilateral triangle, 60, 60, 60, between O and D has to be the same between R and D. So this is 10. So because we've got these nice equilateral triangles that don't look like equilateral triangles because I can't draw them, this radius is going to be the same as each side of this regular hexagon. So we now know that the radius is 10. This is a radius here, R, and this is a side. It just happens that we have 6 equilateral triangles that make up this hexagon. Because we took 360, we divided it by 6 to find this to be 60. We know that these angles have to be the same. They're consecutive angles or consecutive radii coming from the center. So we end up with a 60, 60, 60 triangle. So now we can look at this little subsection here. We have a 30, 60, 90 triangle here. So from our previous lessons, we learned that this part of the triangle will be root 3 times the shorter leg. So OP, I'm going to see if I can squeeze this in somewhere over here. OP will be equal to 5 root 3. The shorter side times root 3. So this section here, well, that's the apothem we were looking for. So we know that apothem is 5 root 3. So now we can get back to this final thing over here. Area is going to be 1/2 the apothem, so 5 root 3 times the perimeter, which we found up over here. It's 60, I promise. So 60, 1/2 the apothem times the perimeter. Well, I cannot draw 60. 60. And if we do a little bit of math here, we learn that the area is 150 root 3. Again, there were no units here, so let's just say that this side was, I don't know, a centimeter, right? From here to here was 10 centimeters. So we need to put units on the answer here. This would be square centimeters right there. That's it for today. We'll see you next time.